Hello, today we're going to talk about linear models for higher order initial value problems. In particular, we'll just focus on second order. So the first one we're going to talk about is a mass on a spring. So if we have a mass attached to a spring, then gravity is going to pull that mass downward, but there will be some sort of restoring force that the spring has that allows it to bounce back up once the mass is removed. And when these two forces are equal, the restoring force and the gravity force, then the mass will be at equilibrium. If the mass is displaced from equilibrium, then it's going to oscillate up and down. And this can actually be modeled by a second order constant coefficient linear differential equation. And it's this one right here, where we have mx double prime plus beta x prime plus kx equals 0. In this equation, m is going to be the mass of the object. Beta is going to be any damping that might be occurring in your problem. And just so that we're all really clear on this, beta is a constant of damping, while beta times x prime is a damping force. Okay, so one's a constant, one's a force. And then k is a spring constant. Okay, so we can think of damping as any sort of friction. Friction can be caused by your mass in your spring being submerged in some sort of liquid, or anything that's going to cause that motion to not just go on forever and ever and ever. Okay, something that would make the motion stop over time. If there's no damping, then we say beta must be equal to 0. Okay, so we're going to have problems that talk about damping, and then we're going to have problems that don't even mention it. In the problems where they're not even mentioning any damping, that's when beta is equal to 0. If beta is not equal to 0, then we are working with a damped system. Okay, because beta is a damping constant, that means we have a damped system. When beta was equal to 0, that means there was no damping, which meant we were working in an undamped system. Okay. So because this is a linear constant coefficient differential equation, we should be able to solve it very easily just using the methods that we already learned before. Your book, and I will also do the same thing because your book does it, but your book goes into a lot of explanation of renaming constants, and I think it can get a little bit confusing when we are able to solve these differential equations without knowing anything about mass spring systems at all. So we should just do that and then gather the information we have from our solution. But I'll walk through everything. So below is a derivation of each scenario. We're going to talk about the undamped case first and then the damped case. And just remember that the above differential equation that I gave up here, that works for both cases. You just undamped, beta is going to be 0, damped, beta is not equal to 0. Okay? As long as we have the mass, the damping constant, and the spring constant, and any initial conditions, we can solve this problem. All right? Now, in the case where the motion of the mass continues indefinitely, like never stops, almost like it's in a vacuum, we say that we're dealing with simple harmonic motion, or also known as free undamped motion. And this just means no damping. Or maybe in a vacuum. Okay, it's not a realistic case, but it is a case that we consider. And so when we consider this, we've got the natural position of the spring. You know, I've got this little drawing here. We have a natural position, like if the spring was just hanging, this would be how long it was. But if we attach a mass, that's going to kind of change the length that the spring is stretched by some s amount right here. And we say that the mass is in equilibrium if it's just hanging there. And when it's in equilibrium, the mass times g, where g is the gravitational force, will be equal to the spring constant times the amount of stretch that shows from having the mass attached to it. And that's actually what's going to allow us to build our differential equation, okay? And then when it's in motion, of course, the spring is going to be going up and down, up and down. It's going to be crossing that equilibrium line over and over again, okay? So in our case, in the undamped motion, the only force acting on the mass is gravity. Now the force of gravity is given by F equals mass times the gravitational constant G, where there are two different ways we can look at G, okay? G is either equal to 32 feet per second squared, those are the English units, or G is equal to 9.8 meters per second squared, those are the metric units. You got to figure out which one to use based on whether you were given information about feet or meters, okay? Technically, the English one is like 32.2, but our book uses 32. And so to make your calculations come out the same as theirs, using 32 will help. Mass is not the same as weight. And so we got to know the difference between mass and weight. Mass is given to us either in slugs, if we're dealing with English units, or kilograms, if we have metric units. Force is the same as weight, okay? So force has units of pounds if we're dealing with English, or newtons if we're dealing with metric, okay? So the solution, x of t, that's going to denote the displacement of the mass from equilibrium at any given time, right? X will be a function of t, so we'll have a function. But if we pick like a time, I don't know, t equals 3 seconds, we could figure out what the displacement is from equilibrium. So it's customary, and this is really, really important, to agree that down is positive and up is negative. Okay, so a positive displacement is below the equilibrium point, and a negative displacement is above. That's a pretty big subtlety, and if you forget about it, what's going to happen is your initial conditions will give you the wrong signs, okay? All right, now according to Hooke's law, the restoring force of the spring is proportional to the displacement and acts in the opposite direction from the displacement. So the restoring force is given by this minus k, that's our spring constant, times this s plus x, where s is the amount of stretch an object of mass m will cause to a spring when not in motion. The spring constant k is given in pounds per foot if we're dealing with English units, or in newtons per meter if we're dealing with metric. And to find k, we're going to have to solve, okay, we have this force. Force is equal to mass times the acceleration due to gravity, the gravitational constant g, but the mass times g is also equal to ks. And so we can get a formula there that relates force and the spring constant. Okay, and so then we can get this nice little formula here. So if we know how much the spring has stretched and we know the force, then we can find the spring constant. All right. Force will either be given to us or we'll have to convert to find it, but force should always be in terms of pounds or newtons, no matter what. So if you need to refresh yourself as you go through this section on the different units that show up, definitely read through this first page again. Okay. Now, by Newton's second law, the sum of the forces of a system, gravity plus the restoring force, is equal to the mass times acceleration. So that's this first equation that I have right here. And then we can play around with this a little bit, and we can distribute the minus kx, the minus k to the x plus s. But because mg and ks are equal, that means these two terms are going to go to 0. mg and ks are equal, so I have one of them positive, one of them negative, then that sum goes to 0. So m times x double prime, that's the mass times acceleration, is just going to equal minus k times x. And so that gives us this differential equation, mx double prime plus kx equals 0. Notice there's no beta x prime. So this is just the undamped case of mx double prime plus beta x prime plus kx equals 0. This is the only difference at all. Now here's where things get a little bit weird, and you don't need to do this. But I talk about it because your book does, and we do get some information from it. It's just that we don't need to change our constant names in our differential equation in order to figure this out. Okay, so we have a new variable. It's called the angular or circular frequency, and its name is omega. Looks like a W, but it's an omega. And omega is going to equal the square root of k over m. So what they've done here is they've taken this original differential equation and divided everything by m. So x double prime plus k over mx is equal to 0. Okay? And then they're letting omega squared replace k over m. And again, there's no real good reason to do this, but they do it for, I guess, for the ease of having one letter to look at when we're looking at a generic case, okay? So we just have x double prime plus k over m times x is equal to 0. And then what they say is omega squared will equal k over m. So that's why omega is the square root of k over m. And so then they're treating the differential equation to be in this form, x double prime plus omega squared x equals 0. And then the auxiliary equation would be m squared plus omega squared equals 0, and that would have complex solutions. Okay, now kind of another way to look at this that I want to talk about right here is that if we were just to solve this one, the auxiliary equation would be, let's see, we should probably do this. I'm going to if we let x equal e to the r t, okay, because x is a function of t, and I don't want to reuse m because m is mass, so I'm just switching to r's. Then the auxiliary equation would be m r squared plus k r equals 0. Is that right? No r. So just plus k equals 0. And so then r squared would equal a minus k over m. But k is a spring constant that's positive. M is a mass, that's positive. And so k over m is a positive fraction. So we're saying r squared is equal to this negative fraction, which would mean that r was equal to I, or I should say plus or minus I square roots of k over m. Okay, so this is synonymous to what they're doing with the omega squared. I just want you to see how they're related and how doing it isn't actually all that necessary. The roots that we get, what they call the omega, m is equal to plus or minus I omega. That omega value, that's like the multiplier that we put in to the angles of the cosine and the sine, because we have these complex solutions to the auxiliary equation. But omega is just the square root of k over m, and we would have got that anyway. They're equal. So whether we know the value of omega as omega or as the square root of k over m doesn't really matter a whole lot. Okay? What is important is that omega is the angular frequency. So if we're asked anything about the angular frequency, then we know it's omega, and omega is the square root of k over m. Okay? I'm sorry if that was long-winded. I just don't want that to be a confusion for anybody or to be a sticking point. Okay? So once we, set up our differential equation, because this is a differential equations class, you don't just memorize the solution. You will set up a differential equation each time. You will solve it using the methods you've learned, and then you will form your solution, and then you can apply your initial conditions. So our solutions in the undamped case will always be x of t is c1 cosine of omega t plus c2 sine of omega t, with x of 0 equal to some x naught. So that's the place, the position at time 0. And then the x prime of 0 is equal to x1. So that's the velocity at time 0, or in other words, how fast the spring was pushed off. So this solution gives a position of the mass at any point in time. And once we apply those initial conditions, then we can answer questions about the oscillations, any questions that they come up with. So I've made this list of some important things to know, and it's a lot. It's a whole lot, but I just wanted to take what was in the book and summarize it in one place, so you don't have to keep going back and trying to find all these things. So here they are. The period of motion. You're going to get asked questions about this. That's just the time it takes to complete one oscillation. Can be found by calculating big T equals 2 pi over omega. This would be the same as 2 pi over the square root of k over m. Okay? The frequency is going to be f, and that's equal to 1 over the period of motion. Or in other words, take the period of motion and reciprocate it, and you've got omega over 2 pi. That's just the number of cycles that get completed each second. So the period is the time it takes to complete one oscillation, and the frequency is how many oscillations are completed each second. Okay? X of 0 equals x naught is the initial displacement. And then I've made a note about signs. If x naught is less than 0, then the displacement is above the equilibrium. If x naught is greater than 0, then the displacement is below the equilibrium. What's going to happen for you is you're going to be told things like the displacement is 2 feet below the equilibrium. You have to interpret that x naught equals positive 2 at that point. Okay? And then if x naught is equal to 0, then there's no displacement from equilibrium. X prime of 0 is equal to x1, and this is the initial velocity. And if x1, the initial velocity, is less than 0, then the mass has an imparted upward velocity. If x1 is positive, then the mass has an imparted downward velocity. And if x1 is equal to 0, then the mass is released from rest. Okay. Now, after we have, we have our initial conditions all set, and we go ahead and we can then solve for C1 and C2, we can find more things out about our equation of motion. Now, if both C1 and C2 are non-zero, then the amplitude of the motion is not obvious, okay? And so what we'll have to do is convert the equation of motion to a simpler form. And this is only once we know C1 and C2. Then we'll be able to convert our equation of motion to x of t equals a times sine of omega t plus phi, where phi is called a phase angle, and it's like the shift of the sine function. Now the amplitude will be found by taking the sum of squares of C1 and C2 and then taking a square root of that. That will tell you, how high the maximum distance above and below equilibrium that your equation of motion will hit. Sine of phi is equal to C1 over A, and cosine of phi is equal to C2 over A, which means then that tangent to phi is C1 over C2, and this can allow us to solve for phi. Phi is just tangent inverse of C1 over C2. But here my note is to pay attention to the quadrant of where C2 and C1 are, right? C2, it looks like, is corresponding kind of with the X value, and C1 is corresponding with the Y value, because sine corresponds with Y, cosine corresponds with X, okay? And we also know that when we are looking at tangent, the ratio that we get is the opposite over the adjacent, or in other words, the sine value or the Y value over the X value. Now, some instructors in science and engineering prefer the cosine form of this simpler form. We don't use this in this class, but I just bring it up so that you see it and you're aware of it, because you might see it online and think, oh, I'm going to use that instead. Don't. That's not the one we use in this class, okay? We use this one, 5. Okay, the minute you start using a different form, it changes the way we do our work to answer some questions. And so you want to be really careful of that. When finding phi, you must be sure that you're finding the angle in the correct quadrant. The signs of C1 and C2 will allow you to figure this out. And then you just have to remember that tangent is a pi periodic function. It is not 2 pi periodic like sine and cosine. Okay? All right, with all that said, we can finally get to an example. So it's a lot of talking to get to the examples here. All right, in here, a mass weighing 32 pounds stretches a spring 2 feet. Before I go any further, I want to write down the information that I was just given. Okay, we are told that the mass weighs 32 pounds. That's the force. Okay, a mass is either in slugs or it is in kilograms. It is not going to be in pounds. And that's something you're going to have to get used to. If you've taken your physics classes, you're probably already used to that. The other information is that this mass stretches a spring 2 feet. Well, that information is that S is equal to 2 feet. Okay, so from this bit of information, we know 2 things. Number 1, we are working with the English system. And number 2, we need to find mass. Okay, so we have 2 formulas that are going to help us. We know that F is equal to mg, which means that m is equal to F over g. Okay, that's our mass. And our force is the 32 pounds. And because we're working with the English system, g, the acceleration due to gravity, is 32 feet per second squared. And this is going to simplify to be 1, and the unit simplification is a slug. Okay? The next thing we can use is that the force is equal to Ks, where K is the spring constant and S is the amount of stretch the mass caused to the spring. So this means, if this equality is true, that the spring constant can be found by looking at the force over the stretch. So we're looking at the 32 pounds over the 2 feet. And that simplifies to be 16 pounds per foot. Okay? And so at this point, the differential equation, notice I haven't even gotten to anything else in the problem yet. What they gave me in the first sentence was enough to do a lot. In my differential equation, I'm going to use the form that's good for both damped and undamped. We have mx double prime plus beta x prime plus k x is equal to 0, where mass is equal to 1, beta is equal to 0, and k is equal to 16. Okay, so when I rewrite, this is just x double prime plus 16x is equal to 0. That's my differential equation for the equation of motion. Now, reading further. Determine the amplitude and period of motion if the mass is initially released from a point 1 foot above the equilibrium position with an upward velocity of 2 feet per second. So I'm not going to determine the amplitude and period of motion yet, but I am going to use the information they gave me about the initial release and the upward velocity. So the initial release is from a point 1 foot above equilibrium. That means that x of 0 is equal to a -1. The upward velocity of 2 feet per second tells me that x prime of 0 is equal to its upward velocity, so that's a -2 feet per second. Okay? So now I have my differential equation with the initial conditions. This is my IVP. So this is the IVP to solve. All right, so let's go ahead and solve it. All right, I'm going back to the methods used from 4.3 when we learned how to work with homogeneous equations. We let x equal e to the RT, where I'm using r because m has already been used, all right? And then x double prime will get an r squared in it. So we get an r squared e to the RT plus 16 e to the RT is 0. We factor out the e to the RT, and that leaves behind r squared plus 16, and that's all equal to 0. So our auxiliary equation is r squared plus 16 is 0, which means that r is equal to plus or minus 4i. Okay? So I didn't have to rename anything omega at this point. However, what I know from what I got about r is that omega, right, omega is going to equal 4. That's the information I got here based on what we talked about before with building up our differential equation. Okay? So now that I know that, I know that the equation of motion is always the solution to the differential equation. Okay, and so that's going to be x of t is c1 cosine of 4t plus c2 sine of 4t. Okay, now I have to apply the initial conditions, but I need the derivative of my equation of motion. And so I take that. X prime of t will be -4, will equal -4, hold on, sine, sorry, -4 c1 sine of 4t plus 4 c2 cosine of 4t. Okay, so we're going to apply x of 0 is -1. That's going to give me c1 cosine of 0 is 1 plus c2 sine of 0 is 0. This is all equal to -1, which means c1 is -1. Then I apply x prime of 0 is equal to -2. And so this gives me -4 c1 sine of 0 is 0 plus 4 c2 cosine of 0 is 1. And this is all equal to -2. And this means that c2 is equal to a -1/2. And so x of t is equal to a negative cosine of 4t plus or minus 1/2 sine of 4t. Okay? Now, this is the equation of motion, but this was not what we were being asked for. We needed to do all this work to get x of t so that we can answer some questions. Let's see what those were. Determine the amplitude and period of motion. Okay. Amplitude. A is equal to the square root of c1 squared plus c2 squared So I'm going to plug in C1 and C2 and square them. So this is the square root of 1 plus a quarter, which is the square root of 5 over 4, or the square root of 5 divided by 2. That's our amplitude. The period of motion, that's t, and t is equal to 2 pi over omega, where up above I did highlight that omega is 4. And so this is 2 pi over 4, which simplifies to just be pi over 2. And then let's see what else was there. How many complete cycles will the mass have completed at the end of 4 seconds? Okay. Let's see. How do we want to word this? So the frequency is equal to the number of cycles per second. And that's equal to 1 over t, which is equal to 2 over pi. Okay? So that's how many cycles we would get in a second. Okay? So the number of cycles in how many seconds? 4 pi seconds is going to be 2 over pi times the 4 pi seconds. And so that's going to simplify to be 8 cycles. That one's kind of weird because the question was about frequency, but it took it a little bit further. And so we have to go back to the definition of like, what is frequency? It's the number of cycles per second. And so if I get 2 over pi cycles in 1 second, then, I could just, if I needed to know how many there were in 2 seconds, I would just multiply by 2. If I need to know how many there are in 5 seconds, I multiply by 5. And if I need to know how many cycles there are in 4 pi seconds, I just multiply by 4 pi. Seems weird, but that's all there is. And that answers all the questions that were asked of us. So we got our period of motion, we got our amplitude, we got our equation of motion, our amplitude, our period of motion, and the number of cycles in 4 pi seconds. All right, next topic. Now we're dealing with the case where beta is not 0. These are the damped situations. And there's we have a whole nother thing where the book decides that we're going to make this a little bit more confusing by renaming all of our letters that we've already named. Okay, but let's start from the top. So this is a case where there's some sort of friction in the system that makes it so that oscillations will just die off after a certain point in time. This is ideal, like think about when you're driving your car and you hit a big bump. You do not want the oscillations to go on forever after you hit that bump. So you have good springs in your car or shocks in your car, and they have the proper damping so that you don't feel like a really hard, bump when you hit the bump, but you also don't have a car that's just going to act like a boat and go up and down forever afterwards. So it's like a sweet spot on the damping. So free damped motion is the name of our system. And some of the different things that we could think of for types of friction are air resistance, fluid resistance, or some sort of physical damper. The shocks and springs on a car, there's usually some sort of physical container, like a dash pot that's holding the spring, that acts like a damping device. Now, because damping is a friction force, we assume that it's proportional to the velocity of the mass and it acts in the opposite direction. So the damping force, and I brought this up before and I'll bring it up again, the damping force is minus beta x prime for some positive damping constant, beta. So if we apply Newton's second law to say that the sum of the forces are equal to the mass times acceleration, and then we bring over to everything to one side of the equation, we get back that original differential equation that I had brought up before. Bringing it into standard form is not necessary. The book does this, and I'm doing it as well to explain what the book is doing. But to solve this differential equation, we can solve from here. There's actually no need for us to go into all the things that they start talking about. But the reason they do this is so that they have an easier way to talk about the different cases that we get, like having repeated real solutions or unique real solutions or complex solutions to the system. So I'll humor them and go along with this. So if we get this into standard form, that means we're going to divide everything by an m. And then we've got this beta m here, beta over m, and this k over m. And this is what they rename. The beta over m is going to be 2 lambda. And fortunately, the k over m is still omega squared. Okay? That didn't change from the undamped case. And so when we make that change and then we solve using the quadratic formula on the auxiliary equation, where m has been introduced again, but m is not the mass, m is the root, the variable in the auxiliary equation. Our solutions are going to be of the form m1 and m2 are both equal to negative lambda, but then there's this plus or minus the square root of lambda squared minus omega squared. Okay. Now, if we were to deal with that from up here, then I would have roots r would be equal to, and I would use my quadratic formula, minus b would be minus beta, plus or minus the square root of b squared, so that's beta squared, minus 4, and a is m, and c is k, and that's all divided by 2m. Okay, so we would just have this form. And so it looks like like we can get lost in lambdas and omegas by trying to like change things into the form that they've got, or we can just simply know what it means when we have 2 real unique solutions or 2 real repeated solutions or complex solutions. Okay, it's your choice. But ultimately, you're going to solve the auxiliary equation however you decide to solve it. We should get the same solutions, and then we need to look at the discriminant on our solutions and decide what form we have for our solutions. Okay, so let's go over that part. If the discriminant is positive, we get 2 real unique solutions. And now remember that in each of these cases, the solution have the form. Sorry, I want to go up to here. Well, all of these cases, we let x equal some e to the rt. Okay, in their case where they've switched over to 2 lambda and omega squared, they used m instead of r, so you can think of it still the same. But our solutions should be this exponential form, just like they were in 4.3 when we dealt with the homogeneous equations. Okay, so we get 2 real unique solutions. That means we know the multiplier in the exponential of the e function. Okay. But the physicality of it is that the system is overdamped. And when something's overdamped, that means that that's like hitting something while you're driving, and it's like a real hard thud. Like there are no oscillations. You just hit and it's hard and it hurts. Okay. Overdamped systems simply move back toward the equilibrium position as displacement decays to 0 over time. There are 2 real unique solutions to the auxiliary equation, m1 and m2, or if you use it, do it the way I'm doing it, r1 and r2. But the solution form, regardless, will be x of t is c1 e to the m1t plus c2 e to the m2t. If the discriminant is equal to 0, then we get two real repeating solutions. And the physicality that's happening here is that the system is critically damped. And that's very similar to the overdamped system. It does not oscillate. However, if the damping is reduced even the slightest bit, oscillatory behavior will start. Okay, so it's that your damping constant is like putting you right on the boundary between no movement and oscillatory movement. So when we have that one repeating solution, the form will be x of t is c1 e to the m1t plus c2t e to the m1t. Last case 3, is where we have complex solutions, and that means that the system is underdamped. Not enough damping is going on. These systems do oscillate, and we'll see in the solution form we've got sines and cosines, and so those cause oscillatory motion. However, the exponential term that is in front of the solution form, that's going to dominate eventually. Notice it's e to the minus lambda t, where lambda is positive, so that minus sign says that's a decaying exponential function. And so it's going to go to 0. And that's, kind of, we could think of that physically, where we've got something that starts off with oscillations, but then slowly over time, because of the exponential multiplier, the oscillations just die out. Okay? But the form is the same as it was before. We have e to the minus lambda t. And remember, that was the alpha plus beta I form that we had. So in this case, lambda is acting like the alpha. And then times in quantity c1 cosine of the square root of omega squared minus lambda squared times t. So that square root of omega squared minus lambda squared, that was our beta before. But we're not using beta in these problems at all because beta is the damping factor. So it's like there are too many letters going on here. And that's part of the reason for renaming things. And then plus c2 sine of the square root of omega squared minus lambda squared times t. Of course, just putting my own 2 cents in here, when the solutions are complex, I find it simpler to consider the case where m1 is alpha plus I beta and m2 is alpha minus I beta, and then the solution form is the same as it was in 4.3. X of t is e to the alpha t times c1 cosine of beta t plus c2 sine of beta t. And just to stress that this beta, this is not the damping constant beta. Okay. So also the form of our solution now more closely matches what we learned in the previous chapter. And that's what I like about going back to like what we know instead of adding more complexity to a problem that might already feel a little complex just because it's new. But the solving techniques are not new, okay? So in all 3 cases, since there is damping, as t goes to infinity, x of t will go to 0. So the system always approaches the equilibrium position over time. All right. Let's apply this to an example. In this example, we have a 4-foot spring and it measures 8 feet long after a mass weighing 8 pounds is attached to it. The medium through which the mass moves offers a damping force numerically equal to the square root of 2 times the instantaneous velocity. Okay. From those 2 sentences, I want to write down what I know. I have a 4-foot spring that measures 8 feet long after a mass is attached to it. So S, that's the amount that the spring stretches. It's going to be 8 feet minus 4 feet, which is 4 feet. Okay, the mass weighs 8 pounds. So we don't say that the mass is 8 pounds. The mass weighs 8 pounds. So that means we were given force, which is 8 pounds. And this is very similar to what we did in the previous problem where we're given F and S and we need to find M and K. So that means we do the same thing. So we have F is equal to mg, right? And we need to know mass. So we're going to take the force and divide it by the gravitational constant. The force is 8 pounds. The gravitational constant is 32 feet per second squared. This simplifies to be 1/4 of a slug. We also know that force is equal to the spring constant K times the amount of stretch. So we can solve for K and say K is equal to the force divided by that stretch. And so that's 8 pounds over the 4 feet. And that will simplify to 2 pounds per foot. Okay? And so we have M, we have K. Now, the medium through which the mass moves offers a damping force numerically equal to square root of 2 times the instantaneous velocity. What this is saying, the damping force is beta x prime. And this is equal to the square root of 2 times the instantaneous velocity, x prime. And so together, this says beta is equal to the square root of 2. So I've got my beta, I've got my m, I've got my k. I can build my differential equation. It's going to be mx double prime plus beta x prime plus kx equals 0. And let's put everything in there. M was 1/4 x double prime plus beta, which is the square root of 2 x prime, plus k, which was 2x, is equal to 0. I'll just do one last thing to simplify it, multiply everything by 4. X double prime plus 4 square root of 2 x prime plus 8x is 0. Okay, now let's see what else they've given us. Find the equation of motion if the mass is initially released from the equilibrium position with the released from equilibrium position. That tells me x prime of 0 is 0, right? It's not above or below equilibrium, it's at equilibrium, so there's no displacement. Sorry, that's not x prime, that's x of 0. Downward velocity of 5 feet per second, that's saying that the initial velocity at time 0 is downward, which means positive 5 feet per second. Okay, so I have my differential equation and I have my initial conditions. This right here is the IVP to solve. Okay, so we solve it. I think I gave myself room on the next page. Oh, good. Okay, so let's see, solve the DE. We're going to let x equal e to the RT. So I plug everything in. I'm going to get r squared e to the RT plus 4 square root 2 r e to the RT plus 8 e to the RT is 0 when I substitute in x equals e to the RT and its derivatives. Factoring out the e to the RT leaves behind r squared plus 4 square root 2 plus 8. That's equal to 0. And I'm going to need to use the quadratic formula in order to solve that. So r is equal to minus b minus 4 times square root 2 plus or minus the square root of b squared. That will be 16 times 2, which is 32, minus 4 times 1 times 8, all divided by 2. So underneath the radical, I have 32 minus 32, which is 0. So this all simplifies down to a negative 2 root 2. So I have real repeating solutions. And so what that means is that x of t is equal to c1 e to the negative 2 square root 2t. That's for the first solution. Plus c2, and it's going to be repeating, so I'll put a t multiplier, times e to the negative 2 square root 2 times t. All right, that's my equation of motion, and I need its derivative as well. So x prime of t is negative 2 square root 2 c1 e to the negative 2 square root 2 t plus c2 e to the negative 2 square root 2 t minus 2 square root 2 c2t e to the minus 2 square root 2 t. Just barely got that in there. All right, and I'm going to apply my initial conditions. X of 0 is 0. I plug in 0 everywhere for t, and I get c1 times 1 plus c2 times 0 is 0, which means c1 is 0. And then x prime of 0 equals 5. So plugging in 0 for t everywhere, I get negative 2 square root 2 c1 times 1 plus c2 times 1, and then minus 0 because we're going to plug in t equals 0, and then this is all equal to 5. And so this tells me minus 2 square root 2 c1 plus c2 is 5, but c1 was 0, so c2 is 5. Okay, so finally, the equation of motion is x of t equals 5t e to the minus 2 square root 2 t. Okay? Now, what were they asking us for? Find the time at which the mass attains its extreme displacement from the equilibrium position, and what is the position of the mass at this instant? Okay, so we want to find the time and the position for extreme displacement. Extreme displacement, I start thinking about derivatives, right? Because we've got oscillatory motion here, so things go up and they go down, so we have maximums, right? We want extreme displacement, just to summarize it, extreme displacement equals absolute max or min, possibly. Okay, and that means we need to solve x prime of t is equal to 0, because we want to know where is the tangent line flat, horizontal. In other words, it has a slope of 0, because that correlates with our derivative. Okay, so I need x prime of t, and then I can set it equal to 0 and I can solve. So x prime is 5 e to the minus 2 square root 2 t minus 10 square root 2 t e to the minus 2 square root 2 t. I can factor this. I can pull out a 5, and I can pull out an e to the minus 2 square root 2 t, and that leaves behind a 1 minus 2 square root 2 t, and set that all equal to 0. Now the exponential function will never be equal to 0. So that means that 1 minus 2 square root 2t must be 0. So t is 1 over 2 square root 2, which is approximately 0.35 seconds. That's the time when we get extreme displacement. The position, I should say that here. So this is the time of extreme displacement. And the position the position of extreme displacement, position is x of t, but we just need to find x of t when t is 1 over 2 square root of 2. I don't plug in the 0.35 because that was an approximation. The exact time is 1 over 2 square root 2. So when I plug that into the equation of motion, I get 5 over 2 square root 2 e to the negative 1. And then that is approximately 0.65 feet. Okay. And another way to confirm this, like this is the work that needs to be done to show that you found it, but another way to confirm that you got the right thing, look at a graph of x of t and on Desmos and pinpoint where the maximum is, and you'll see these approximate values there. Okay. One last topic here that I want to bring up. I'm not going to go into extreme detail on it. I bring it up because some people may see these in other classes. I only assign 1 or 2 homework problems, the easiest ones I can find. But series circuit analogs are important, and you're going to see them in E&M. And so it's nice if you actually see them in a differential equations class first. So if I of t represents current in the LRC series electrical circuit, remember L is inductance, R is resistance, and C is capacitance. We did talk about these like first order problems way back in chapter 3, okay? But if I of t represents the current in the LRC series electrical circuit, then the voltage drops across the inductor, resistor, and capacitor is shown in this figure below. Okay, so we have a picture of a circuit with an inductor, resistor, and a capacitor. By Kirchhoff's second law, the sum of these voltages is going to equal the voltage E of t impressed on the circuit, and it leads to this first order differential equation here. L times di dt plus Ri plus 1 over Cq is equal to E of t. And again, this isn't new. We learned about this in chapter 3. But we also learned that I is dq dt. So if we make a substitution, it's going to lead to another linear constant coefficient, ODE. We replace I with dq dt, which means we replace di dt with the second derivative, dq squared dt squared. I don't have my square there on the t. For the second derivative. Okay, and so this is just extending what we learned in chapter 3. And so instead of looking at the current, we're looking at the charge. Now, if we let E of t be equal to 0, the voltage is equal to 0, and we compare this to what we've learned about the mass spring system with damping, that was the mx double prime plus beta x prime plus kx equals 0, then we can see some relationships. So the charge Q is corresponding to the displacement in a mass spring system. The inductance L is corresponding to the mass from a mass spring system. The resistance R corresponds to the damping constant beta, and the reciprocal of the capacitance 1 over C is corresponding with the spring constant K. So we would solve the differential equation the same way we would solve any linear constant coefficient dE. Okay, no new methods are learned. And because there's always some amount of resistance, though, we will always have problems that are not equal to 0. So when solving this differential equation, where I've kind of written it in the simpler prime notation, we will have one of 3 situations occurring. An overdamped circuit, if there are 2 unique real solutions, a critically damped circuit, if there are 2 real repeating solutions, and an underdamped circuit, if there are 2 complex solutions. Solving any of these problems is totally analogous to what we did with the mass spring systems. Just identify all the constants you need to put in your initial values, solve the dE, and then answer any questions you're being asked. In all the cases, there will be an exponential multiplier in the general solution, be this e to the minus capital RT over 2L. You don't need to memorize it. It'll just work out in your solving process. But notice that as t goes to infinity in this form, that whole charge is going to go to 0. And in the undamped case, the charge on the capacitor will approach 0 in an oscillatory manner. And that just means the capacitor's charging and discharging. It's like on and off as t goes to infinity. Okay, so again, the problems are analogous to what we did with mass spring systems. There are, one or two problems in the homework that are fairly straightforward to set up. In other words, like they give you L, they give you R, they give you C. Plug them in, solve, and then answer any questions that are being asked. As always, if you have any questions while doing your work, please reach out.